Let's take a look at the problems on the first test review for differential equations. So in problem number 1, I have three integration problems that look very similar in that they are all three rational functions. And so they look similar in that they all have a 2 in the numerator and they have some sort of variable in the denominator. But we're just comparing how are they alike, how are they different. So in the first problem on problem number 1, I can simply rewrite that with my integral properties, coefficient out of the way, 1 over x dx. It is a simple or normal integration problem. So the antiderivative of 1 over x is ln absolute value of x plus c. Don't forget the absolute value. Don't forget the c. So that's problem number 1. The second problem in problem number 1 is 2 over x to the 1/2 power. So it might, well, there is a variable in the denominator, but we're not going to have any sort of ln here because the antiderivative of 1 over x to the first power is ln. So the second problem in number 1 requires a rewrite to move that variable to the numerator and make it x to the negative 1/2 power. So this is really all about math eyes and knowing the right tool for the right job. So now when I find the antiderivative, I'm going to increase the power by 1, and that takes me to the 1/2 power. I'm going to divide by 1/2, which is multiplied by 2, times the 2 that's already there. So I get 4x to the 1/2 plus c. Don't forget the c. And in letter C, the third part of number 1, we have a variable in the denominator to the first degree. However, it's not just plain x, there's a binomial, there's a coefficient of x, so my math eyes are telling me probably need to go with a u substitution. U is equal to 3x plus 4. The derivative is 3 dx. I don't need that 3, so I'm going to make it a 1/3 du equal to dx by dividing. I'm going to do my substitution, so my new integral is going to be 1/3. I'm going to take the coefficient of 2 out front and make that 2/3. So then when I substitute 3x plus 4 and when I substitute u in place of 3x plus 4, I get 1 over u du. The antiderivative is 2/3 ln absolute value of u. So I'm going to bring back or resubstitute 3x plus 4 in place of u, and that will give me 2/3 ln absolute value 3x plus 4 plus c. So that's problem number 1, and notice that they look alike, but we had to do something a little bit different for each part. So in problem number 2, how are they alike? How are they different? Well, I noticed that in the first 2 problems there is a binomial of 2x plus 3, but in the first problem that binomial is in the numerator, and in the second problem that binomial is in the denominator. So these two are reciprocals of each other. Wonder how that's going to impact my decisions. And in the third situation I have a binomial, but now it's 2x squared plus 3. So let's go to the first problem. In the first problem, hopefully you realize that there is a monomial denominator, so we can take that apart and rewrite it as 2x over x plus 3 over x dx. And that's going to simplify to be 2 plus 3 over x dx. It's a very normal and simple problem. It's a take apart, our Miss Oliver math. So when we find the antiderivative, we get 2x. The antiderivative of 3 over x is 3 ln absolute value of x. Don't forget the c. Now for problem number 2, we have something different going on because we can't take apart. You can't take apart a binomial denominator. So in this case, I don't know how to integrate it straight out, so that makes me think probably need to go with a u substitution. So u is equal to 2x plus 3. Du is equal to 2 dx. I don't need that 2, so I'm going to divide it to the other side. And so when I look at my information, I can see that I can replace 2x plus 3 with a u. I can replace, oops, I dropped my du, I see that now. I can replace dx with a 1/2 du, but daggone, there's a stubborn x right there. So I'm going to go back to the first line and I'm going to solve that for x, or get x by itself. So I have u minus 3 over 2 equal to x. So now when I make the substitution, so pay close attention, there is a 1/2 right here, and then there is another 1/2 right here. So when I do my rewrite, I'm going to have a 1/2 coefficient in the front multiplied by, I'm going to go ahead and get that other 1/2 right here, coefficient in the front. I'm going to rewrite my integral. So in place of the x, I'm going to substitute the u minus 3. Remember, let me erase that. Got a stray mark there. I already took the over 2 out front. So I have a u minus 3 in the numerator, and in the denominator I'm replacing 2x plus 3 with a u du. So that's 1/4 of the integral. So we've turned it now into another take apart. So u over u is 1, and 3 over u stays 3 over u. The antiderivative of 1 in terms of u is u. The antiderivative of 3 over u is 3, dropped my 3, ln, absolute value of u plus c. So when I resubstitute, I end up with 1/4 of u is 2x plus 3 minus, be careful because that 1/4 has to go to all the terms. So that'll be 3 ln absolute value of 2x plus 3, squeeze that in there, plus c. I could distribute the 4 through and make it 1/4 and 3/4, or I can leave it as is. So that is the second of the 3 problems. I'm going to reset my screen and do the third problem. So in the third problem, as we talked about earlier, or as I talked about earlier, you cannot take apart this denominator. So I'm thinking we're looking at another u substitution situation. So u equal the denominator of 2x squared plus 3. du is equal to 4x dx. I'm going to divide both sides by 4. X dx. This one I don't have, the x is not stubborn this time because I have the x dx. So the second one was stubborn x, the third one is not stubborn x. Then my rewrite becomes 1/4 antiderivative of 1 over u du. Antiderivative of 1 over u gives me ln, absolute value of u plus c. Resubstitute 1/4 ln of 2x squared plus 3. You know what I'm going to say. Don't forget the c. So that's the third part of problem number 2. All right, let's take a look at problem number 3. So in problem number 3, they don't all necessarily look alike. I do notice that I'm seeing a 4x squared plus 3x. So first one, when I look at the first problem in number 3, it looks pretty normal. It looks like reverse chain rule. The antiderivative of 4x squared is going to be 4x cubed over 3. That was easy. The antiderivative of 3x will be 3x squared over 2. That was easy. Don't forget the c. So, gotta love those ones that are just normal, easy, and not much drama. Second problem, so let's get rid of that. Okay, I'm going to approach this how I think a student might approach it. A student might go, ooh, look at that inside function. So u is equal to 4x squared plus 3x. This is not a wrong thing to do, but it's going to dead end, and you'll see. The derivative is du on the left side, and on the right side, I get 8x plus 3 dx. Now, when you look back at that original problem, we are not seeing any 8x plus 3 or an 8 or a 3 or anything like that. So it's like I've got way too much stuff, more stuff than I actually can replace. So this means that U substitution is not the way to go. It just dead-ended for me. So I just back up, and that's what problem solving is about. It's about trying something, and if it doesn't work, thinking of another strategy. So think about all your math tools, and the key, hopefully by now you've already figured it out, to success is doing what the problem tells you to do. And in this case, it says, hey, just square this out. When you square this binomial, you will get 16x to the fourth plus 24x to the third plus 9x squared. Now, a note. If you can't square that binomial by looking at it and doing what I just did, write the binomial twice. There is no shame. It just takes a little bit longer. There is no shame in writing the binomial twice and showing your FOIL and taking your time to do that squaring. So, when I find the antiderivative here, I get 16x to the fifth over 5. In other words, this turns into a pretty normal problem. 24x to the fourth over 4 is 6x to the fourth. 9x cubed over 3 will be 3x cubed. And guess what? Yeah, don't forget the c. So that's the first two problems of number 3. All right, I'm going to clear my annotations just to make room for that last problem. And so now I see a trig situation. So, and I see an E situation. So there are a variety of things that I could choose for U. Now I'm going to choose the wrong thing first just to show you the dead ending so that you can see that if you choose the wrong thing, you back up and try again. So I'm going to choose secant squared x. So U is equal to secant square x. This is the wrong choice. And let's see how I can find out that it is the wrong choice. The derivative, be careful, we got some chain rule action going on here. Remember that secant of x squared. So the derivative of secant squared x is 2 secant x, leave the inside alone, so that's the first part of the chain rule, number 1, times the derivative of secant x, which is secant x tangent x, which when simplified gives me 2 secant squared tangent x. Now remember, you might be getting excited and thinking, oh, we do have a secant squared. Well, we've already compensated for that. Oh, we have a tangent x, but it's up here with the e. This is dead ending. It's not going anywhere, and it's not helpful. It wasn't wrong to think about it. It wasn't wrong to try it. But if that's where you leave it, that would be wrong. So the other thing that I'm going to consider as a possibility for u is the power of e. So in this case, u is tangent x. Du, the derivative of tangent, is secant squared x dx. Now we're getting somewhere. So we can do a rewrite. Secant squared x right here, and the dx gets replaced with du. Tangent x gets replaced with u. And we got to love e to the u. The antiderivative of e to the u is e to the u. Make the resubstitution, so we get e to the tangent x plus c. Pretty straightforward. Going on to the next page, we have a free response question. I can't remember, this problem might use a calculator, or I think at least part B is going to need a calculator. And I'll pull my calculator out here in a second. The rate, so you know from all of our discussions in class that reading is the most important thing. The rate of consumption of cola is given by S of t. So S of t is the rate of cola consumption. You got to remember what this function is so you can know what to do with it when they ask you to do something. Where S is measured in billions of gallons per year, so there's that rate, it's how many billions of gallons of cola are consumed per year, and T is measured in years from the beginning. So this is important right here. T is measured in years from the beginning of 1980. So in other words, 1980 is t equal to 0. So we're not going to use the 1980. We're going to use the t equals 0. And I figured that out when they said from the beginning, years from the beginning. In letter A, they tell us that the consumption rate doubles every 5 years. And the consumption rate at the beginning of 1980 was 6 billion gallons per year. So in other words, we have an initial condition, an order pair at 1980. S of 0 is 6. They're also telling me that the consumption rate doubles every 5 years. So if the consumption rate in 1980 was 6 billion gallons per year, then we know that 5 years later that the consumption rate was 12 billion gallons per year. Just putting that information together. Before we start trying to do the work and solve the problem, you have to record everything that we know to figure out how to proceed. All right, so our job here is to find C and K. So what I'm going to do is I'm going to take my equation, and they told me that S of 0, well, let's just do this. So let's clear that. All right, I'm going to underline these in 2 different colors. So I'm going to underline, don't underline with an eraser. I'm going to underline the 0, 6 in red and the 5, 12 in black. So I'm going to set up 2 different equations. And what I'm going to do is I'm going to substitute the 0 and the 6 into my equation. And I'm going to substitute the 5 and 12 into my equation. Now I'm going to actually create myself more workspace here. All right, so I'm going to take the point that I create, the 0, 6, which I did in red, and substitute the 0 and the 6 into the given equation. So the output is 6. So 6 is equal to CE, and remember, T is 0, so 0 times K is 0, so we have CE equal to 6. Well, maybe I'll just go ahead and show that. CE to the K, which we don't know, times T, which is 0. So that's the same thing as 6 equal to C E to the 0. E to the 0 is 1, so yay, that was pretty easy to figure out the value of C. So we have part of our problem settled. Now I'm going to use the second point to substitute into my same equation. So I have the output of 12 equal to CE to the K, which is 5. I'm sorry, T is 5. Well, I can just do that. So T is 5, and I'm solving for K. Now remember, we just found that C is equal to 6, so I can substitute that in and get C equal to 6E to the 5K. Divide both sides by 6, and I get 2 equal to 5K. All right, and let's call on our best Algebra 2 skills. I'm going to take the ln of both sides in order to bring down, my power. So that'll give me 5K times the ln of E. That's using log properties. We know that ln and E are inverse operations, so they do undo each other. So K, dividing both sides by 5, is equal to ln of 2 over 5. So my equation is S of t is equal to 6, which is the initial condition, E, K is equal to ln of 2 over 5, times t. All right, so that takes care of, let's see, we're finding C and K. Probably will need that, so I'm going to write it actually over here because I'm going to have to get rid of my little chalkboard or get rid of some of this work. So 6E ln of 2 over 5 times t is equal to S of t. Okay, so let me get rid of this work so that I can go to part B. May need to get rid of the box, we'll see. All right, in part B, we are finding the average rate of consumption of cola for the 10-year period beginning January 1st, 1983, and we need to indicate units of measure. All right, so I think we're probably going to need our calculator to evaluate this. Now, remember, when you see, it doesn't say average rate of change, it says average rate. So this is where we want to insert our phrase value of. So I'm finding the average value of the rate, and the rate is S of t. So we're finding the average value of S of t. It tells you right here for a 10-year period. So I'm going to 1 over b minus a is going to be the 10-year period. I'm going to divide by the 10 years. I'm going to accumulate starting at, now it tells me here that we're starting in January 1st, 1983. And remember, t was years from 1980. So this would be the 3rd year from 1980 to the 13th. If it's going to be a 10-year period, 13 years, we're going to accumulate S of t dt. Okay, I'm going to grab my calculator to show you how to handle that. All right, so as you can see, I've pulled out my calculator, and the only difference that you might see is if you have the older model calculator. I've taught you how to type in when you get the fint instead of the symbols that you're going to see with mine. So I'm literally going, I hate that phrase, where I'm going to type in exactly what I see on my paper, which is 1/10 of. So I'm going to start, I can either type 1/10 in parentheses, or since I know that 1/10 is 0.1, I might just type it like that. So there's my 1/10. To get the integration, I'm going to do a math. I'm going to select number 9, which is the fint. And if you have an older model calculator and you have not written down the how to type it in with when it puts fint, please contact me and I'll help you with that. All right, so my low bound is 3, my high bound is 13, and this is really important for everyone, regardless of your calculators, being really careful on how we're typing in the function. So over on the left-hand side of my screen, remember I wrote down the function, and I'm going to be really careful about how I type in that power of ln of 2 over 5 times t. Right, so I'm going to have 6, and then my e, there are a couple of places you can get it. One is right here above the division symbol in blue, and the other place is above the ln symbol in blue. So I'm going to do second ln. All right, now I need to type in a power. Now, since I have a coefficient of ln of 2 over 5, I'm going to put parentheses around that just to be on the safe side. So I have ln of 2, close that parenthesis, divided by 5, close that parenthesis. Okay, so look at that very carefully. I have parentheses around the 2 because the calculator put in a parenthesis. I had to close that, and then I closed the parenthesis that I opened, so I have my fraction separated, and now I'm going to have my variable. We're going to type an x and not a t. All right, then I'm going to get out of there, x. All right, so the calculator is going to accumulate the area and divide by 10, and you see that I get 19.680. I got to remember that because I need 3 decimal places. Oops, I didn't mean to totally close that, but that's okay. So, whoa, stop it, you dumb, stupid pen. Okay, let's try it again. So I have 19.680. Now look at the units. Billion, gallons. It goes back to per year. Why? If you're still struggling with units, we divide it by time, which is years. We have S of t, which is already gallons per year. dt, that's time multiplied by years. So these years can divide out these years, and you get gallons, billions of gallons per year. Okay? All right, let me clear that and go to part C. So in part C, we are, fun times. We are creating, using the trapezoidal rule with 4 subdivisions to estimate. So let's think about how we're going to do that. So our job is to estimate or approximate the definite integral. We might use the calculator to do some number calculations for us, but let's think about a trapezoidal approximation. The area of a trapezoid is 1/2 of the height multiplied by base number 1 plus base number 2. We're going to do 4 different trapezoids. Right, so I'm going to start with trapezoid number 1. Trapezoid number 1, I'm going to take my formula. There's 1/2 the height. Now, if we're going to go from 5 to 7, so my interval is 7 minus 5, and I'm going to divide that interval into 4 parts. So 7 minus 5 is 2, divided into 4 parts means that each of my heights of each of my trapezoids is a 1/2. So understand, I'll do this in blue, this 1/2 comes from the formula for the area of a trapezoid, the blue 1/2. The black 1/2 is the height of each of my trapezoids. So I have 1/2 the height, and now I'm going to multiply by base number 1. So base number 1 would be cola consumption at 5 plus cola consumption, and remember we're moving half a unit because our base is 0.5, S of 5.5. That is the area of trapezoid number 1. For trapezoid number 2, I'm going to do the formula of area of a trapezoid, 1/2. The common height is 1/2 times, and now I'm going to get the height for, or the base 1 is S of 5.5. I'm going to move a half a unit and go to S of 6. That's trapezoid number 2. All right, I'm going to wrap this around because I'm running out of space. The third trapezoid is 1/2 from the formula for the area of a trapezoid times 1/2, which in this case is the common height. Base number 1 is S of 6. Base number 2 is S of 6.5. And then the last trapezoid, trapezoid number 4, goes back to 1/2 from the formula for the area of a trapezoid times 1/2, which is the common height of all of the trapezoids in this case. Base number 1 is S of 6.5 plus S of 7, and notice we ended up where we were supposed to end up. Now, I'm not going to take the time to pull the calculator out to do these calculations. However, I will say this. In this particular case, I think it would be much wiser if you had the function into y number 1, and I already forgot what our original, it was 6e, I think you can do it, again. Remember it, ln of 2 over 5t. It might be, it's a great idea to put that function into y1, and then you can go on the home screen and you can call up the calculations. So if you look at your answers in the packet, you will see that the calculation turns out to be 27.668 billion gallons. So I can talk about that in class if you're struggling with the calculator use. It's just more time consuming and you have to be careful typing than anything else. Okay, let's go on to part D. So in part D, we are using correct units to explain the meaning of 5 to 7 of S of t dt. Recall that S of t is a rate, and when you integrate a rate, you lose the rate. So let's first of all talk about units. We were in billions of gallons per year. That was our original scenario for S of t, units for S of t, if we're going to integrate that rate, we're going to lose the gallons. So what we're going to be measuring is billions of cola. Okay, let me redo that. That made no sense whatsoever. I was like, what in the world are you talking about right now? I think I said one thing and wrote something different, which is, as you know, par for the course. So S of t, let's try that again, is in billions of gallons per year. Okay, I'm back in the land of the living. So when we integrate a rate, we lose the rate, and we're going to lose the years, which means we're going to have billions of gallons of cola. So I would say something like the definite integral, let's type it because it's easier to read, so we'll do it right here. All right, so I would say something like the definite integral indicates the change in the cola consumption. Indicates, I'm writing as I type, I haven't worked this out ahead, indicates the billions, I like this better, of gallons of cola consumed from 5 years from 1980, from 1985 to 1987. All right, so I think I like that. Yeah, I do. Okay, let's move on. I'm going to get rid of those annotations and get rid of this writing. I think I am. The little engine that could. I think I can. All right. So letter E. Letter E, we are finding the derivative of a definite integral. So I'm going to remember our 3 steps. Take out the t, put in the new function, multiply by the derivative of the new function. Notice that I have a lower bound of a constant 5, which is exactly what I want. Let me write my S of t up here. So S of t is 6e to the ln of 2 over 5 times t. So derivative of a definite integral. Step number 1, take out the t. So where the t is, parentheses, step 1. Step 2, put in the new function, which in this case is 6x squared. Step 3, multiply by the derivative, not as a power, but down here, of the new function. The new function is 6x squared, and the derivative of 6x squared is 12x. So we can multiply 6 times 12 and get 72x e to the ln of, ln of 2 over 5 times 6x squared. And finally, the last problem is, maybe I have it on a separate page. Nope. Maybe I don't have the last problem on here. There, nope. I'll write it on here. Let's see if I go down if I have it. Nope. The last problem is to solve the differential equation of 4x plus dx dt equal to 60. So remember, it's a differential equation and we need to separate our variables. So the first thing I'm going to do is I'm going to subtract the 4x to the right hand side and make that 60 minus 4x. I don't want to multiply the dt over because remember, we want the x's together and the t's together. So I think what I'm going to do is, notice I have a common factor here. I can divide or factor a 4 out of the 60 and the 4x. That'll leave me with 15 minus x. So now I think I have something that's easier to separate because I can divide both sides by 15 minus x. So I'm dividing the 15 minus x to the left-hand side. I'm going to leave the 4 on the right-hand side, so I divided the 15 minus x. I'm going to keep the 4 and multiply the dt to the right-hand side with the constant. So I have x is separated and t separated. I'm going to find the antiderivative on both sides. So just a little investigation on the left side. If u is equal to 15 minus x, du is equal to negative, so I need to compensate for that, like that. All right, so the antiderivative of the left-hand side is going to become negative ln absolute value of 15 minus x. Now I can do that as a complete u substitution on the side if needed. On the right-hand side, when I find the antiderivative of 4 in terms of t, I get 4t, whoops, boom, 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 4t plus c. Okay, and we are trying to solve for x. We're trying to get x by itself. Trying to decide what I want to do here. I think what I want to do at this point, I'm trying to decide if I want to solve for c or if I want to try to get x by itself. I'll go ahead and get x by itself. So that'll give me ln. I'm going to divide both sides by a negative. Now, interestingly enough, that'll give me negative 4t, and it'll still be plus c. That might bother some of you, but remember c is a constant and it absorbs. We don't know what that number is. We don't even know if it's positive or negative to begin with. So it still stays a plus c. I'm going to, as students might say, e both sides. I'm going to raise both sides to the power of e. So I get 15 minus x is equal to e to the negative 4t plus c. You know that we can use exponent properties, exponent properties to rewrite that as c e to the negative 4t. That'll give me negative x is equal to c e to the negative 4t minus 15. Divide both sides by negative 1, and x is equal to, remember that c can absorb that negative, you don't have to have a negative, plus 15. And so, sorry, I'm eating something because it's right before lunch. So, or during lunch. That is the solution to the differential equation. Hope this helps.